Welcome to my lab away from the lab. What I have here is a piece of rusty plate from what's called a telepost. Those are those posts in your basement that are used to jack up the ceiling. Here's my Christmas telepost acting on a ceiling in the living room that has been under repair for some years, so that is our cat-proof Christmas tree until I finish this ceiling. And its sister ceiling is in here. So let's go back to this telepost plate. It's been in contact with concrete for years, so it's rusted. The post is steel of some kind. Steel is iron with some carbon in it. Well, this iron is iron oxide, and it's Fe plus 3. The normal red rust you see is iron 3 oxide. So if iron is plus 3, oxygen is minus 2, then this thing would be Fe2O3 we're seeing. And you can see it's structurally useless material. It falls apart like a dust. Let's clean this plate up and have another look. Now that I've cleaned and dried the plate, you can see that it's fairly evenly rusted. There's no loose rust on it now. And on the underside, you can see some of the original coating that was on the plate is still there. It's still structurally quite sound. It's just had some erosion over the years sitting on a concrete floor. I can show you one in the garage that I painted it first, and it's totally rust-free after many more years. But damp and concrete do not like metal. We're going to do something with this. We're going to throw it in a pot of boiling water. I have an old cast iron frying pan here, and I've stuck this plate in, and I'm going to boil it for a few minutes. In the meantime, I want to show you another piece of metal I have. You can see here what looks like a cast iron plate. This is actually not cast iron. This is a steel skillet. This is steel, that's aluminum. What you can see about aluminum is it's not quite as shiny as steel. Here's a stainless steel mixing bowl, or at least coated in it. And my water softener is at a salt right now, so you can see the water spotting because of the mineral in the Orangeville water supply. So this is aluminum. This steel plate was this color when I first got it. It's just a cheap Coleman camping plate from Canadian Tire. Why is it black? Well, it's black because over the years I've coated it in butter or oil and baked it in the oven. And the basics of oil and sugar and fats is carbon. When you destroy them in the heat, you leave the carbon behind. Not pure carbon, it's a complex carbon compound, but gradually over time I've built up this carbon layer. And carbon is fairly slippery, particularly graphite. It's an excellent lubricant. If you don't believe me, rub a pencil between your fingertips like this and feel it, and it's like super lubrication. So this is a really long-term coating of carbon that makes this non-stick. And it's the same thing you do with cast ironware. And so of course, I don't want anybody scrubbing the life out of this and taking the carbon layer off, because it's many years that I built this up and it's basically non-stick. Now lately it got left out and there's a little bit of patch of rust here, so I'll just oil it up, bake it in the oven again. First, I disconnect my smoke detectors, or better yet, I do it on the barbecue, and you get this super nice layer of carbon that's super slippery. Got a nice vigorous boil on, cooking up that steel plate. It's really good, lots of iron. It's a bit chewy, but pretty soon we're going to have iron 2 for dinner. Alrighty, I've taken the iron out of the pot of boiling water, And you can see now it's changed its color fairly dramatically. On the reverse side, I've rubbed a little bit of oil onto it, which is what's done to highlight it. And you can see now we formed what's called black oxide. And the two, we've simply forced the iron from one valence state to another. Now, if we look up in your textbook, iron is Fe2O3 because oxygen is -2 and iron is +3. So if I were to draw the Lewis dot diagram here, we'd go Fe ... Fe ... and then it's going to take 3 O's. And that's why I like the colloquially notation of the empties. 2 empties here. And then you can draw your things over. Who wants to see that mess? Well, what happened to this black oxide? What's gone on there? A great deal of the iron got forced into the +2 state. And that's what made it go black. It's not quite that simple. A lot of it got left in the +3, and the formula, you could do it. I might show it as an extension, but it's definitely not grade 9 or grade 10. This formula is actually a weirdie. It's Fe3O4 because it's got a mix of the 2 and 3. And I'll put up an extension for those of you that want to try it. But this is called magnetite. And it's magnetic, where this iron rust is not. This iron rust is very, what's called friable. If I take a fork here, I can scrape it off, right? Get piles of red dust. It expands in volume. So if you look at red rust, it's much thicker and puffier. So it breaks things apart. This is why a rusty nail is impossible to remove from wood. It can expand something like 27%. Magnetite does not expand, so the coating of that black oxide is very flat. And if I do what's called carding, if I scrape the metal, retreat it, scrape the metal, retreat it, it'll eventually form smooth patches, and you get this lovely black oxide coating. You oil it, do it again, and you get that gunmetal black. It's not paint, it's a thick layer of oxide. And this oxide is more air sealed than this one. So this will keep rusting till it decays to nothing. This will stop to a point. All right, if I leave it out, it'll turn red and form that again. Magnetite is one of the most common magnetic minerals on Earth. And this black oxide was what was once used on audio cassettes. On the actual tape, they used iron oxide particles to magnetize the recording. And oddly enough, we have it in our brains. We have magnetite deposits in our brain, and they know birds and some bacteria have it, and they use it as onboard compasses. So it's possible we have some biological leftover that gives us some sense of direction. And that's why men won't listen for directions, because we believe we have that. The thing is, our natural world now is so full of magnetism that I doubt very much our natural sense of direction. It's stomped on by everything around us. So there you go. That's how we can force a valence state change on iron.